Tonight, imagine yourself behind the wheel of a car, cruising down an endless highway beneath a canopy of stars. Your speed is steady at 65 miles per hour, the hum of the engine a constant companion as the painted lines blur past. This is comfortable, familiar territory. You've driven this speed countless times. But tonight, we're taking this earthly velocity and pointing it toward the heavens. Tonight, we're asking a deceptively simple question that will take us on a journey through time and space, unlike anything you've imagined. How long would it take to drive to each planet in our solar system at highway speed? The question seems almost whimsical at first. After all, we can't actually build a highway through the void of space, can't roll down the windows and feel the solar wind on our faces as we cruise past Venus or navigate the asteroid belt like some cosmic truck stop. Yet this thought experiment does something profound. It takes the incomprehensible and makes it human. It transforms the abstract numbers you might find in astronomy textbooks into something that touches our lived experience. Because we all know what 65 miles per hour feels like. We know the rhythm of a long road trip, the way hours accumulate, the patience required to traverse even terrestrial distances. Space, in its raw astronomical measurements, can feel sterile. Millions of miles, billions of kilometers, astronomical units. These numbers cascade over us without meaning, too large to grip with our minds. But time, measured in familiar increments, speaks to us differently. Days, weeks, years, decades, these are the currencies of human life, and when we use them to measure cosmic distances, something magical happens. The universe becomes, if not smaller, at least more relatable, more real. So buckle up, check your mirrors, adjust your seat for what will be, without question, the longest drive of your existence, many times over. We're about to embark on a journey that will span not just the breadth of our planetary neighborhood, but the very limits of human patience, human lifespans, and human imagination. We'll travel from the scorched surface of Mercury to the frozen blue depths of Neptune, 1 mile at a time, 1 hour at a time, watching the odometer click forward relentlessly as years turn to decades, and decades stretch into something beyond the scope of any single human life. This journey will reveal something fundamental about our place in the cosmos. It will show us, in the most visceral way possible, just how alone we are on our pale blue dot, how vast the gulfs between worlds truly are, and how remarkable it is that we've managed to reach even a fraction of these distances with our robotic ambassadors. The highway we're imagining doesn't exist, but the wonder, the isolation, and the grandeur it represents most certainly do. The open road beckons. The universe awaits. Let's begin our impossible journey, one that will test not just our understanding of distance, but our grasp of time itself. Welcome aboard the Cosmic Highway. Destination everywhere. Before we accelerate into the darkness between worlds, we need to understand exactly what speed we're working with. 65 miles per hour might seem straightforward, the kind of number you see on highway signs across America, but when we project this terrestrial velocity into the realm of planetary exploration, it takes on entirely new dimensions. This is the speed where most highway systems find their sweet spot, fast enough to cover distance efficiently, controlled enough to maintain safety. In kilometers per hour, this translates to approximately 104.6. Let's be precise, 104.607 kilometers per hour, though for our purposes, we'll round to 105. This is not a blinding speed in astronomical terms. Our robotic spacecraft travel far faster. New Horizons, one of the swiftest machines humanity has ever built, reached speeds of over 50,000 miles per hour, nearly 800 times our highway cruising pace. But that extraordinary velocity comes at a cost measured in rocket fuel, engineering complexity, and mission budgets that strain the resources of nations. Our thought experiment is more democratic, more human. It asks, what if we could simply drive? What if the journey required nothing more than the patience to maintain pressure on an accelerator and the lifetime or lifetimes needed to cover the distance? At 65 miles per hour, you travel 1,560 miles every day. That's the distance from New York to Denver, from Los Angeles to Seattle, from London to Rome and beyond. Every single day, relentlessly, without stopping. In a year, at this constant pace, you would cover 569,400 miles. That's enough to circle Earth's equator almost 23 times. It's a staggering distance by earthly standards, the kind of mileage that would leave any conventional vehicle a rusted shell, its engine seized, its tires atomized to memory. Yet in the context of interplanetary space, this barely registers. It's a starting point, a baseline from which we can begin to grasp the true scale of our solar neighborhood. Converting this to the metric system gives us 168 hours to cover 1,6,700 kilometers. 38,800 kilometers every week. 2.01 million kilometers every year, marching forward with mechanical precision, the odometer spinning like some meditation on infinity. These numbers will become our reference points, our mileposts in the dark. When we calculate journey times to distant worlds, these annual and daily accumulations will be the foundation upon which we build our understanding. But distance in space isn't measured in miles or kilometers alone. Astronomers use a more elegant unit, the astronomical unit, abbreviated AU. 1 AU is defined as the average distance between Earth and the Sun, roughly 93 million miles or 150 million kilometers. It's a measure that acknowledges the vastness we're dealing with while keeping the numbers manageable. Earth orbits at 1 AU. Mars, at its average distance, sits at about 1.52 AU. Neptune, the most distant planet, orbits at roughly 30 AU. These might seem like small multipliers, but when you're traveling at highway speed, each AU represents an almost unimaginable commitment of time. The speed of light, that ultimate velocity limit woven into the fabric of space-time itself, crosses 1 AU in about 8.3 minutes. Light from the sun takes that long to reach Earth, to warm our faces, to power the photosynthesis that maintains our biosphere. At our humble 65 miles per hour, crossing that same distance would take us 177.6 years. Nearly 2 centuries to traverse what light manages in the time it takes to boil water for tea. This disparity, this vast gulf between what physics permits and what our highway speed allows, sets the stage for everything that follows. Understanding this relationship between speed, distance, and time is crucial for the journey ahead. We need to internalize that space is not empty in the sense of being easily crossable. It's full, densely packed with absence, with void that must be traversed kilometer by kilometer. There are no shortcuts at our velocity, no rest stops where time compresses, just the endless accumulation of miles, the patient mathematics of motion. At 65 miles per hour, you are moving at approximately 95.3 feet every second. You could count 1 Mississippi and you'd be almost 100 feet farther into space. Count to 60 and you've traveled more than a mile. It seems fast in that context, but against the yawning distances between planets, it's glacially, heartbreakingly slow. This is the paradox at the heart of our journey. Highway speed is fast by human standards. It can feel dangerous, thrilling when you're navigating curves or merging into traffic. But in space, that same velocity reveals itself as something else entirely. A study in patience, in the relentless accumulation of small increments across timescales that exceed human lifespans by orders of magnitude. We are about to discover what it means to be fast and slow simultaneously, to move at a rate that would make any terrestrial journey brief but renders cosmic distances into epochs of time. Ready your mind for numbers that will challenge your intuition, for journey times that will make you reconsider what near and far really mean. The engine is running. The road stretches out before us into the dark. Let's see where it leads. Our first destination emerges from the glare of the sun like a ghost. Mercury, the smallest planet in our solar system, the swiftest in its orbit, the world that bears the name of the Roman messenger god for its rapid movement across our sky. This tiny, cratered sphere, only slightly larger than our moon, hurtles around the sun every 88 Earth days, closer to our star than any other planet. It's a world of extremes, roasting at 430 degrees Celsius on its sun-facing side, plunging to negative 173 degrees in the eternal shadows of its poles. No atmosphere to speak of, no moons, just bare rock scarred by billions of years of cosmic bombardment. This is where our cosmic road trip begins, with the closest major world to the Sun, though not, as we'll discover, consistently the closest to Earth. The distance to Mercury fluctuates dramatically because both Mercury and Earth follow elliptical orbits around the Sun. When Mercury reaches what astronomers call inferior conjunction, positioning itself directly between Earth and the Sun, it makes its closest possible approach to our world. At this configuration, Mercury can come within approximately 77 million kilometers, though this varies slightly based on where both planets are in their respective elliptical paths. The record close approach, 77 million kilometers, represents Mercury at its absolute nearest, a cosmic alignment that brings this inner world as close as it can possibly get to our own. Converting this to miles gives us about 48 million miles, a number that sounds vast until we compare it to other planetary distances where it will seem almost intimate. At our highway speed of 65 miles per hour, covering 48 million miles requires a simple but daunting calculation. 48 million divided by 65 gives us roughly 738,461 hours of continuous driving. Now we translate this into more comprehensible units. 738,000 hours divided by 24 hours per day yields approximately 30,769 days. Divide that by 365 days per year, and we arrive at the result, 84.3 years. Let that sink in. To drive to Mercury at its very closest approach would take 84 years and roughly 4 months. An entire human lifetime, from cradle to grave, spent with your foot on the accelerator, watching the distant dot of Mercury grow incrementally larger through your windshield. But Mercury doesn't stay at its closest approach. Far from it. When Mercury swings around to the far side of the Sun from Earth, a configuration called superior conjunction, the distance balloons dramatically. At this point, Earth and Mercury can be separated by as much as 222 million kilometers, or roughly 138 million miles. The journey time to reach Mercury at this maximum distance is proportionally longer. 138 million miles at 65 miles per hour equals 2,123,076 hours, which works out to 88,462 days, which translates to 242 years. 2.5 centuries. 12 generations of a single family could be born and die over the course of this drive. The United States would age from its founding to the present day. You could watch entire civilizations rise and reshape themselves while maintaining your steady speed toward the distant speck of Mercury. Recent research has revealed something counterintuitive about Mercury's position in our solar system. While Venus makes closer approaches to Earth than any other planet, Mercury spends more time close to Earth on average than any other world. This seems paradoxical at first. How can Mercury be closest on average when Venus gets closer? The answer lies in orbital mechanics. Venus and Earth, being on relatively close orbits, spend significant time on opposite sides of the Sun from each other, separated by the full diameter of Venus's orbit plus Earth's orbit. Mercury, orbiting much closer to the Sun, stays relatively near Earth more consistently because its orbit doesn't carry it as far away when it's on the Sun's far side. Over time, averaged across all possible positions, Mercury spends more of its orbital period in Earth's general neighborhood than any other planet. This makes Mercury not just our nearest neighbor at certain times, but our most constant companion in a statistical sense. Imagine the journey unfolding in real time. You leave Earth, pointing your vehicle toward that bright morning star visible just before dawn or just after sunset, depending on Mercury's position. The first days pass with Earth shrinking behind you. The first weeks see our planet reduced to a bright star. The first months, and you're truly alone, in a way no human has ever been, surrounded by the absolute black of space, the Sun growing incrementally brighter ahead of you as you fall toward the inner solar system. Years pass. You could learn a language, master an instrument, write a novel, raise a child from birth to adulthood, and still be less than halfway to Mercury. The psychological weight of such a journey staggers the imagination. No stops for gas, no scenic overlooks, no changing landscape except the slow adjustment of planetary positions against the background stars. Mercury itself would begin as just a point of light, indistinguishable from a bright star. As months stretched into years, you might start to perceive it as a tiny disk through binoculars, then through the windshield. After decades, it would finally reveal itself as a world, cratered, gray-brown, marred by enormous impact basins like Caloris Planitia, which stretches 1,550 kilometers across. You'd see the planet's curious rotation, spinning 3 times for every 2 orbits around the Sun, creating strange effects where the Sun appears to rise, set, and rise again from certain locations. On Mercury's surface, you'd watch it grow from a dot to a disk to a world, knowing that every second of every minute of every hour of every day and week and month and year brought you exactly 95 feet closer. Progress measured in inches and feet when the distance is measured in millions of miles. The average distance to Mercury, accounting for the various positions in both orbits, sits somewhere around 100 million kilometers or 62 million miles. This middle ground requires approximately 108 years of continuous travel, more than a century. An entire long human life, from Victorian England to the modern age, from the first automobiles to spacecraft, spent in transit to this single nearby world. And we must remember, this is the closest planet to the Sun, one of our nearest neighbors, a world we've successfully sent robot probes to study. NASA's Messenger spacecraft orbited Mercury for years, beaming back detailed maps and measurements. It reached Mercury not in a century, but in years, using sophisticated orbital mechanics and gravitational assists from Venus and Earth itself to build up the velocity needed to match Mercury's rapid solar orbit. Our highway speed journey puts into stark relief what actual space exploration accomplishes. The New Horizons probe, flying at speeds approaching 50,000 miles per hour, covered in months what would take us lifetimes at our cruising pace. The difference between human patience and spacecraft engineering becomes a gulf measured in generations. Yet there's something valuable in contemplating the slower journey. It forces us to feel the distance in our bones, to understand that Mercury, visible to the naked eye from Earth, twinkling in the twilight sky, is nevertheless impossibly far away for any casual voyage. The ancients saw this swift world dance around the Sun and named it for their fastest god. We see it through modern eyes and recognize that even this nearest world requires a commitment of time that exceeds what any single human can offer. The highway to Mercury is long, measured not in exit numbers but in decades, not in rest areas but in generations. And Mercury is just the beginning. As Mercury fades in your rearview mirror after what might have been the longest journey of multiple lifetimes, our attention turns outward to a brighter beacon. Venus, Earth's sister planet, the morning and evening star, the most brilliant natural object in our sky save for the Sun and Moon, hangs before us in space like a promise and a warning. Here is a world almost identical to Earth in size, yet transformed by runaway greenhouse effects into an infernal realm where lead would melt on the surface and atmospheric pressure would crush a submarine. Venus rotates slowly backward, its day longer than its year, shrouded eternally in thick clouds of sulfuric acid that reflect sunlight with such intensity that Venus outshines every star in our night sky. Ancient civilizations worshipped this planet as a goddess of love and beauty, never suspecting the hellscape lurking beneath those lustrous clouds. The distance to Venus presents a different challenge than Mercury's eccentric orbit. Venus orbits the Sun at an average distance of 108 million kilometers compared to Earth's 150 million. This relatively small difference in orbital radii means that when Venus passes between Earth and the Sun, a configuration called inferior conjunction, it becomes the closest planet to Earth. At this moment of nearest approach, Venus can come within approximately 38 to 40 million kilometers of our world. The closest recorded approach in modern times was in January 2022, when Venus came within just under 40 million kilometers. In miles, this translates to roughly 24.8 million at the closest modern approach, though historically, Venus has come slightly nearer. 24.8 million miles at 65 miles per hour requires 381,538 hours of driving. That's 15,897 days, which equals 43.6 years. 43 years and roughly 7 months to reach Venus at its closest approach, driving continuously without pause. This is shorter than the trip to Mercury at its nearest, making Venus genuinely our closest planetary neighbor when the alignment is favorable. 43 years is still more than half a human lifetime, a journey that would span from young adulthood to approaching retirement age, from the first moon landing to the age of private space stations, from the dawn of the internet to whatever comes after the technologies we're only beginning to imagine now. But Venus, like Mercury, doesn't maintain this close position. When Venus swings around to superior conjunction, positioned on the far side of the Sun from Earth, the distance explodes to approximately 261 million kilometers or 162 million miles. The journey to reach Venus at this maximum separation requires 2,492,308 hours, which equals 103,846 days, which translates to 284 years, nearly 3 centuries. Longer even than the worst-case scenario for Mercury. You could travel from the founding of America through the Civil War, both world wars, the space age, and into a far future we can barely conceptualize, all while maintaining your steady speed toward Venus. The planet would spend most of this time invisible, lost in the glare of the Sun, though you would know it was there, beyond that blinding fusion furnace, waiting at the end of your multi-generational journey. The average distance to Venus, accounting for its orbit around the Sun and the varying positions relative to Earth, settles at approximately 68 million kilometers or 42 million miles. This middling distance requires 646,153 hours, translating to 26,923 days, which equals 73.8 years. Nearly 3/4 of a century, slightly less than the worst-case Mercury journey, but still an epoch of human time. You could be born, grow up, have children, see them grow up and have children of their own, and pass away of old age, all while traveling to Venus at highway speed. Venus's orbit creates a fascinating rhythm with Earth. Every 584 days on average, Venus catches up to Earth as both worlds orbit the Sun, reaching inferior conjunction and making its closest approach. This happens because Venus completes one orbit every 224.7 Earth days, while Earth takes 365.25. Venus moves faster on the inside track, lapping Earth periodically in their endless race around the Sun. Over 8 Earth years, Venus completes almost exactly 13 orbits, creating a geometric pattern that early astronomers called the pentagram of Venus, as the successive closest approaches trace out a 5-pointed star when plotted against the background of stars. This celestial geometry adds an aesthetic dimension to the mathematics of orbital mechanics, reminding us that the universe doesn't just follow laws, it creates beauty in the process. Imagine leaving Earth toward Venus at an opportune moment when the two planets are approaching one of those conjunctions that bring them close together. At first, Venus would shine brilliantly in your sky, perhaps appearing near the moon in the evening twilight or morning dawn. As you traveled, watching that bright point grow imperceptibly larger, Venus would go through phases like our moon. When Venus is far from Earth, we see it as a small, full disk. As it approaches, swinging between Earth and the Sun, it grows larger but becomes a thinner crescent, the sunlit side turning away from us as the planet's night side approaches. Galileo's observation of these phases in the 17th century provided crucial evidence that planets orbit the Sun rather than Earth, a revolutionary insight that reshaped our understanding of our place in the cosmos. Your journey would span these phase changes, watching Venus transform from full to crescent and back over the years and decades. You'd see the planet grow from a brilliant point to a visible disk to a world that filled your vision. That world would be terrible and beautiful. Dense clouds the color of old bone, moving rapidly around the planet, driven by winds that reach hurricane speeds in the upper atmosphere, even though the surface sees barely a breath of air movement. If you could penetrate those clouds somehow, you'd glimpse a landscape of volcanic plains, highland regions, impact craters partially obscured by lava flows, all bathed in an eerie orange glow, from sunlight filtered through the thick atmosphere. The surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, maintained by a carbon dioxide atmosphere 90 times denser than Earth's at sea level. It's the solar system's most extreme greenhouse, a runaway effect that transformed what might once have been an Earth-like world with oceans into the furnace we observe today. The journey to Venus at highway speed would give you time to contemplate this transformation. Venus and Earth, so similar in size and composition, took wildly different evolutionary paths. Scientists believe Venus might have had liquid water oceans in its distant past before the greenhouse effect ran away and boiled them into space. Was there life on that ancient Venus? Did primitive organisms swim in those vanished seas before the planet's climate tipped into irreversible hell? We don't know, and may never know, but the decades-long drive would offer ample time to ponder these questions, to imagine that lost world and wonder what subtle factors determined that Earth would become a paradise of life while Venus became an inferno. The clouds of Venus, those beautiful sulfuric acid aerosols that make the planet so bright, would eventually dominate your view as the years accumulated. Scientists have detected strange patterns in Venus's clouds, unexplained dark patches in ultraviolet light that appear and disappear, hinting at atmospheric chemistry we don't fully understand. Some researchers have even suggested, controversially, that aerial microbes might survive in Venus's upper atmosphere where temperatures and pressures are more benign than the crushing surface conditions. Could life exist in the clouds of Venus? The idea seems fantastical, but extremophiles on Earth thrive in environments we once thought impossible for biology, suggesting that life is more adaptable than we imagined. Your slow approach would let you watch these cloud patterns change over timescales measured in decades, potentially observing phenomena that brief spacecraft flybys might miss. Venus, despite being our closest neighbor, remains in some ways more mysterious than Mars or even the distant outer planets. Its thick clouds hide the surface from direct observation, and its hostile environment destroyed every lander the Soviet Union successfully placed there within hours, or at most a couple of hours of touchdown. The Venera missions showed us glimpses of that alien landscape, panoramic views of flat volcanic plains scattered with rocks before the electronics succumbed to the heat and pressure. Our highway speed journey would take us to a world we can barely explore, a planet that defeats our technology through sheer environmental hostility. 73 years on average, or as little as 43, or as much as 284, all to reach a world that would destroy any conventional vehicle the instant it touched that scorching surface. The Venus journey, more than Mercury's, brings home the strange nature of neighboring planets. Venus is close, genuinely close by solar system standards. You can see it with the naked eye shining brilliantly in Earth's sky. And yet, reaching it at human speeds requires half a lifetime at minimum, multiple lifetimes if the orbital geometry is unfavorable. We are close neighbors in the cosmic sense, but separated by a moat of time and distance that makes casual visiting impossible. As your odometer clicked toward Venus, decade after decade, you'd have time to internalize this lesson. Space is not empty, it's full of distance, and distance at human speeds translates into time measured in generations. The highway to Venus is paved with patience and painted with the slow accumulation of miles that would exhaust the fuel reserves of nations and the lifespan of civilizations. And beyond Venus, the road only gets longer. Having navigated the inner solar system, our cosmic highway now carries us beyond Earth's orbit toward the frontier that has captured human imagination for centuries. Mars, the red planet, fourth from the Sun, half the size of Earth, but somehow more familiar than either Mercury or Venus. Here is a world we've landed rovers upon, a planet whose surface we've mapped in exquisite detail, whose dust storms we've watched from orbit, whose ancient river valleys speak of a wetter, warmer past. Mars has occupied a special place in human culture for millennia. Its ruddy color, associated with war and bloodshed, its apparent retrograde motion across our sky mystifying ancient astronomers. In the modern era, Mars has become the focus of our dreams of expansion, the most likely candidate for the first human footsteps beyond the Earth-Moon system. Mars orbits the Sun at an average distance of 228 million kilometers, 1.52 astronomical units. This places Mars firmly in what we might call the outer solar system's entrance hall, beyond the familiar warmth of Earth's neighborhood, but not yet among the giants. Mars's orbit is more elliptical than Earth's, with the planet ranging from 206.7 million kilometers at perihelion to 249.2 million at aphelion. This eccentricity plays a crucial role in determining how close Mars can come to Earth during what astronomers call oppositions, the events when Earth passes between Mars and the Sun, aligning the three bodies in space. During an opposition, Mars shines at its brightest in Earth's sky, rising in the east as the Sun sets in the west, visible all night long as a brilliant red beacon. But not all oppositions are created equal. When an opposition occurs while Mars is near its perihelion, we get what's called a perihelic opposition, bringing Mars closer to Earth than at any other time. The most famous of these recent perihelic oppositions occurred in August 2003, when Mars came within 55.76 million kilometers of Earth. This was the closest approach in almost 60,000 years, a distance of about 34.65 million miles. The next one won't surpass this record until August 2287, nearly 3 centuries from now, though future close approaches will come relatively near this mark. At 34.65 million miles, traveling at 65 miles per hour would require 533,076 hours of continuous driving. That's 22,211 days, which translates to 60.8 years. Almost 61 years to reach Mars during that historic close approach, traveling without pause, watching the red planet grow from a point of light to a world. 61 years is a substantial portion of a human lifetime, but noticeably shorter than the trips to Mercury or Venus at their nearest approaches. This makes Mars, during favorable oppositions, genuinely more accessible than the inner planets at their average distances, a counterintuitive result that helps explain why Mars has been such a focus of exploration. However, Mars doesn't always cooperate with our desire for proximity. When an opposition occurs while Mars is near its aphelion, the distance remains far greater. The most recent distant opposition occurred in March 2012, placing Mars 62.62 million miles from Earth, nearly twice as far as the 2003 record close approach. At this maximum opposition distance, the journey time stretches to 963,076 hours, or 40,128 days, or 109.9 years. 110 years, roughly speaking, to reach Mars when the orbital geometry works against us. An entire long human life, from beginning to end, spent crossing the gap between worlds. The opposition cycle of Mars repeats with fascinating regularity. Earth catches up to and passes Mars every 26 months, or more precisely, every 780 days on average. This synodic period determines when we can launch missions to Mars most efficiently, creating windows that space agencies use to plan their exploration. The New Horizons spacecraft, though ultimately bound for Pluto and beyond, flew past Jupiter in just 13 months from launch. The various Mars rovers took between 6 and 9 months to reach the red planet, traveling at speeds tens of thousands of miles per hour. Compared to our 65-mile-per-hour cruise, these missions are lightning bolts. But they still represent months of travel, months of systems checks, months of holding collective breath, hoping nothing fails before arrival. The average distance to Mars, accounting for the full range of possible separations as both planets orbit, sits at approximately 140 million miles, or 225 million kilometers. This average requires 2.15 million hours of travel, or 89,583 days, or 245 years. Nearly 2.5 centuries of continuous driving to reach Mars at an average separation. Think about that timescale. From the end of the American Revolution to the present day. From sailing ships and quill pens to supersonic jets and quantum computers. That's the gulf represented by Mars's average distance when traveled at highway speeds. Imagine the journey unfolding. You leave Earth, pointing your vehicle toward that red dot visible in the night sky. The first year passes with Earth receding behind you, the familiar blue and white marble shrinking to a point of light, then vanishing into the sun's glare. Mars remains ahead, not noticeably closer, not visibly growing, just present, patient, waiting. Years accumulate. You could watch a child be born, grow up, attend school, graduate university, start a career, have children of their own, and begin to age, all while you continue toward Mars at your steady pace. Decades blur into routine. The sun remains the dominant object in your sky, never setting, always present, gradually growing slightly smaller as you distance yourself from it, though the change is subtle, requiring years to become apparent. Mars would begin to show detail after many years, transforming from a point to a disk visible through binoculars, then to a clear world visible through your windshield. You'd watch its surface features rotate into view every 24.6 hours, Mars's day being only slightly longer than Earth's. The polar ice caps would become visible, advancing and retreating with Martian seasons. The great volcanoes of the Tharsis region would emerge. Olympus Mons, the largest volcano in the solar system, rising 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Valles Marineris, the Great Canyon system, would become apparent, a scar across the Martian surface that dwarfs Earth's Grand Canyon, stretching 4,000 kilometers long, 200 wide in places, 7 kilometers deep. The color would become more nuanced as you approached. Mars isn't uniformly red. There are darker regions, ancient highlands stained with iron oxide, and brighter areas, younger volcanic plains, and the brilliant white of the polar caps. During certain seasons, massive dust storms engulf the entire planet, turning it a uniform butterscotch color as particles lifted from the surface scatter sunlight. These global dust storms occur unpredictably, and during your decades-long approach, you might witness several, watching the planet's features vanish beneath a planet-wide veil of suspended dust that could persist for months before gradually settling again. Mars has captivated us partly because it seems almost Earth-like. Its day is nearly the same length as ours. It has seasons caused by axial tilt, though they last twice as long due to Mars's longer year. It has polar ice caps that advance and retreat, clouds in its thin atmosphere, dust devils that skitter across its surface, even morning frost in the shaded areas. Scientists have found evidence that liquid water once flowed on Mars's surface, carving channels and filling ancient lake beds. Where there was water, there might have been life. Primitive perhaps, but life nonetheless. The search for fossils of Martian microbes drives much of our current exploration, making Mars not just a destination, but a potential answer to one of humanity's deepest questions. Are we alone? Your 61-year journey during a favorable opposition, or your 110-year journey during an unfavorable one, would give you ample time to contemplate Mars's history. Billions of years ago, Mars had a thicker atmosphere and a warmer climate. Liquid water pooled on its surface. Its core was still molten, generating a magnetic field that protected the atmosphere from the solar wind. Then, gradually, the core cooled and solidified. The magnetic field died. Without that protection, the solar wind stripped away much of the atmosphere, reducing the surface pressure until liquid water could no longer exist. The rivers dried up. The lakes evaporated or froze. Mars transformed from a potentially habitable world into the cold desert we observe today, with an atmosphere less than 1% as dense as Earth's and average temperatures around -63 degrees Celsius. But Mars isn't dead, it's dormant. Seasonal flows of what might be briny water appear on crater walls during warmer months. The planet still experiences volcanic activity, though at rates far slower than in its ancient past. There are hints of methane in the atmosphere, appearing and disappearing mysteriously, potentially indicating either geological processes or, speculatively, biological ones. The possibility that microbial life might still exist in subsurface reservoirs, protected from radiation and harsh surface conditions, remains open. Your long journey to Mars would culminate in reaching a world that represents both a past that might have included life and a future where humanity might establish its first permanent presence beyond Earth. The human fascination with Mars runs deep for good reason. It's the most accessible planet beyond Earth, at least during favorable oppositions. It offers resources that future colonists might exploit: water ice in the polar regions and subsurface, carbon dioxide that could be processed into oxygen, minerals that could supply a Martian industry. The gravity, though only 38% of Earth's, is enough that humans might adapt to it better than the microgravity of space stations or the Moon's 1/6 gravity. Mars represents hope, challenge, and possibility in ways that Mercury's scorched proximity to the Sun or Venus's hellish conditions cannot match. As your vehicle approached Mars after 60-some years or a century of travel, you'd be arriving at humanity's next great frontier. Your journey, measured in a single human lifetime at best, or in multiple lifetimes at worst, would end at a world where we've placed rovers that have traveled for years across its surface, drilled into its rocks, analyzed its soil, searched for signs of organic compounds. Curiosity, perseverance, and their predecessors have given us intimate knowledge of Martian geology, climate, and history, even as they've raised new questions about what happened to make Mars what it is today. The highway to Mars is long, requiring patience measured in decades, but it's a journey that ends at a world that calls to us, that represents both our past curiosity and our future ambitions. As Mars grew to fill your windshield, russet and beautiful and alien, and somehow familiar all at once, you'd know that you'd reached the edge of what we might call the inner solar system. Beyond Mars lies the asteroid belt, then the realm of the giants, where distances multiply and the Sun becomes a distant point of light. The road continues, ever longer, ever colder, into regions where the journey times will challenge not just patience, but the very notion of what a single human lifetime can encompass. Beyond the orbit of Mars, separated by the scattered debris of the asteroid belt, space opens into a new realm. Here, the distances stretch beyond anything we've yet contemplated, and at the center of this outer domain sits Jupiter, the giant that dominates our solar system with a mass greater than all other planets combined. Jupiter is a world of superlatives, the largest planet with a diameter 11 times that of Earth, the fastest spinner, rotating once every 10 hours despite its immense size, the possessor of at least 95 known moons, including 4 large enough to be planets in their own right, had they orbited the Sun independently. The Great Red Spot, a storm system larger than Earth that has raged for at least 350 years, swirls in Jupiter's southern hemisphere. Lightning storms crackle across its atmosphere with energy that dwarfs terrestrial thunderstorms. Radiation belts surrounding the planet bristle with particles intense enough to fry electronics and threaten life. Jupiter orbits the Sun at an average distance of 778 million kilometers, or 5.2 astronomical units. This places Jupiter firmly in the outer solar system, far beyond the rocky terrestrial worlds of the inner regions. The planet's orbit is less eccentric than Mars's, keeping it at relatively consistent distances from the Sun compared to the more variable inner planets. But this consistency doesn't make Jupiter close. When Earth and Jupiter are on the same side of the Sun, reaching what's called opposition, Jupiter makes its nearest approach to Earth. The closest recent opposition occurred in September 2022, when Jupiter came within 591 million kilometers of Earth, or approximately 367 million miles. This was the closest approach since 1963, nearly 60 years earlier. 367 million miles at 65 miles per hour requires 5,646,153 hours of continuous driving. That's 235,256 days, which translates to 644.5 years. 644 years and approximately 6 months to reach Jupiter at its closest approach. Let that timescale settle into your mind. 6.5 centuries. From the Crusades to the Renaissance. From the Black Death to the Industrial Revolution. From the Ming Dynasty to the Space Age. Nearly a full millennium of human history compressed into the journey to Jupiter during its most favorable alignment. When Jupiter reaches the far side of the Sun from Earth, at what's termed conjunction, the distance expands to approximately 968 million kilometers or 601 million miles. At highway speed, this requires 9,246,153 hours, or 385,256 days, or 1,055 years, over 1,000 years. More than a millennium of continuous driving to reach Jupiter when Earth and Jupiter are separated by the Sun. From the time of Leif Erikson's voyages to North America to the present day, from medieval castles and hand-copied manuscripts to skyscrapers and digital information, 40 generations of humans living and dying while the journey continues, unrelenting, toward the giant planet waiting beyond the Sun. The average distance to Jupiter, accounting for all possible orbital positions, sits at approximately 628 million kilometers or 390 million miles. This average distance requires 6 million hours of travel time, or 250,000 days, or 685 years. Nearly 7 centuries of highway driving to reach Jupiter at an average separation. This is a time scale that exceeds not just individual human lives, but entire civilizations. Nations rise and fall in less time. Languages evolve and diverge. Technologies are invented, perfected, and rendered obsolete. And still the journey would continue, mile after mile, hour after hour, decade after decade, century after century. The odometer accumulating numbers that lose meaning in their vastness. Imagine undertaking this journey. You leave Earth, watching our blue world shrink behind you, passing the orbit of Mars after 60 or 100 years, depending on where Mars is in its cycle. The asteroid belt lies ahead, that sparse collection of rocky debris orbiting between Mars and Jupiter. Science fiction often portrays the asteroid belt as a dense field requiring skillful navigation, but the reality is far different. The asteroids are spread across such enormous volume that you could drive straight through the heart of the belt and likely never come within millions of miles of a single asteroid. Space remains empty, black, cold, with only the distant pinpoints of asteroids occasionally visible if you knew precisely where to look. Centuries pass. The Sun behind you shrinks, though imperceptibly slowly. After 100 years of travel, you've covered less than 1/7 of the distance to Jupiter. After 200 years, you're still not halfway there, even during a favorable opposition. After 300 years, Jupiter remains far ahead, though it would have started to show as a definite disk to your instruments, no longer a point of light, but a visible world. The scale of this journey defeats intuition. We can say 644 years, but we cannot truly grasp what that means in lived experience. No human has lived that long. No institution has endured unchanged across such spans. It's a duration that belongs to geology, to evolution, to the slow turning of historical ages, not to the brief flash of individual consciousness. As you continued your impossible journey, watching generations be born, live, and die back on Earth, Jupiter would gradually reveal its majesty. The bands of clouds, alternating zones and belts driven by powerful jet streams, would become apparent. The Great Red Spot would rotate into view every 10 hours as Jupiter spun on its axis. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, would become visible as separate worlds, dancing their own complex orbital patterns around the giant planet. Io, the volcanically active innermost large moon, spewing sulfur compounds into space. Europa, the ice-covered world with a global ocean beneath its frozen shell, one of the most promising locations to search for life beyond Earth. Ganymede, the largest moon in the solar system, bigger than Mercury with its own magnetic field. Callisto, ancient and heavily cratered, a frozen record of the early solar system's violent bombardment era. The sheer scale of Jupiter would become overwhelming as you approached. Earth would fit inside Jupiter's Great Red Spot with room to spare. The planet's volume could contain 1,321 Earths. Its mass, while only 318 times Earth's, is still enormous enough to significantly perturb the orbits of comets and asteroids, earning Jupiter its title as the solar system's vacuum cleaner, capturing or deflecting debris that might otherwise threaten the inner planets. Some scientists believe that, without Jupiter's gravitational influence, Earth might have experienced far more catastrophic impacts, potentially preventing the development of complex life. In this sense, Jupiter is our protector, the giant shepherd maintaining order in our cosmic neighborhood. Your journey to Jupiter would take you through the heliopause in a certain philosophical sense. After 600 years of travel, the Sun would have diminished to a bright star, still the brightest object in the sky, but no longer the overwhelming presence it is from Earth. The solar wind weakens at Jupiter's distance. The planet's powerful magnetic field carves out a magnetosphere that extends millions of kilometers into space, creating a bubble within which Jupiter's influence dominates over the Sun's. Spacecraft entering this region experience intense radiation, with particle energies high enough to damage sensitive electronics. The Juno probe, currently orbiting Jupiter, was specially hardened against this radiation, its trajectory carefully planned to minimize exposure while still gathering data on Jupiter's interior structure, magnetic field, and atmospheric dynamics. Jupiter represents a fundamentally different kind of world than any we've encountered on our journey so far. Mercury, Venus, and Mars are rocky planets with solid surfaces you could, in principle, stand upon, even if the conditions would kill you instantly. Jupiter has no surface. It's a gas giant, composed primarily of hydrogen and helium, with trace amounts of methane, ammonia, water vapor, and other compounds. As you descend into Jupiter's atmosphere, the gas grows denser and hotter, eventually transitioning into metallic hydrogen, a state where the element behaves like a liquid metal under the immense pressure of Jupiter's interior. At the very center, there may be a rocky core, perhaps 10 to 15 times Earth's mass, but this remains uncertain. Jupiter is less a planet in the terrestrial sense and more a failed star, lacking the mass needed to ignite fusion, but sharing hydrogen-helium composition with the Sun. The journey time to Jupiter, 644 years at best, over 1,000 at worst, forces us to confront the true meaning of cosmic distances. Space exploration as we practice it requires velocities that would be suicidal at highway speeds. The Voyager probes, launched in 1977, reached Jupiter in less than 2 years by traveling at speeds around 35,000 miles per hour. Juno, launched in 2011, took 5 years but used a trajectory that included a gravity assist from Earth. Even with advanced propulsion, Jupiter remains years away. At our patient 65 miles per hour, it becomes the destination of civilizations, not individuals, reachable only by the patient accumulation of centuries. As your vehicle finally approached Jupiter after its epic journey, the sense of scale would be overwhelming. You'd be arriving at a world where hurricanes larger than Earth rage perpetually, where lightning bolts 1,000 times more powerful than terrestrial strikes illuminate the night, where auroras brighter than any on Earth shimmer at the poles, powered by volcanic material from Io funneled along magnetic field lines. You'd be reaching the gateway to the outer solar system, the first of the giant planets, the king of worlds. But this triumph would be tempered by the knowledge that the journey has only reached the edge of the truly distant reaches. Saturn awaits beyond, and beyond Saturn, the ice giants Uranus and Neptune, where the distances grow so vast that even our 600-year journey to Jupiter will seem brief by comparison. The highway continues, ever outward, into cold and darkness that would test the resolve of species, not just individuals. If Jupiter represents the gateway to the outer solar system, Saturn marks the threshold of the truly remote. Beyond this ringed giant, the Sun becomes a distant point. Planets become frozen outposts in the dark, and the journey times stretch into spans that challenge even our expanded sense of cosmic duration. Saturn, with its magnificent ring system visible even through small telescopes, has captivated observers since Galileo first glimpsed those rings in 1610, though his primitive instrument showed them only as bulges on either side of the planet. Christian Huygens in 1655 first recognized them as rings, and ever since, Saturn has stood in human imagination as perhaps the most visually stunning object in our solar system, a jewel of ice and cloud hanging in the darkness. Saturn orbits the Sun at an average distance of 1.4 billion kilometers or 9.58 astronomical units. This is nearly twice Jupiter's orbital distance, pushing Saturn deep into the outer solar system's cold regions. The planet itself is the second largest in our solar system, with a diameter 9 times that of Earth, though its mass is only 95 times our world's. This makes Saturn the least dense planet in the solar system. If you could find an ocean large enough, Saturn would float, its density less than that of water. Like Jupiter, Saturn is a gas giant, composed primarily of hydrogen and helium, with a similar lack of solid surface, just increasingly dense atmosphere, transitioning to liquid and metallic hydrogen under pressure. The rings that make Saturn famous are actually quite thin relative to their vast extent. The main ring system stretches from 66,000 to 480,000 kilometers from Saturn's center, yet, in most places, the rings are less than 20 meters thick. They're composed of countless particles ranging from tiny grains to house-sized boulders, all ice or rock covered in ice, orbiting Saturn in a flat plane defined by the planet's equator. The rings cast shadows on Saturn's clouds, and Saturn casts shadows on the rings, creating stunning visual effects that shift with Saturn's 29.5-year orbital period around the Sun. The origin of the rings remains debated, whether they're remnants of a moon torn apart by tidal forces or leftover material from Saturn's formation, but their beauty is undeniable. When Saturn and Earth align at opposition, with Earth positioned between Saturn and the Sun, Saturn makes its closest approach to our world. The distance at closest approach varies slightly with the eccentricities of both orbits, but typically, Saturn comes within approximately 1.2 billion kilometers of Earth at opposition, or about 746 million miles. At 65 miles per hour, covering 746 million miles, requires 11,476,923 hours. That's 478,205 days, which translates to 1,310 years. 1,310 years to reach Saturn at its nearest approach, more than 13 centuries of continuous travel. Let that sink in for a moment. 1,300 years. From the time of Charlemagne being crowned Holy Roman Emperor to the present day. From the Viking Age through the Crusades, the Renaissance, the Age of Exploration, the Industrial Revolution, the World Wars, and into our current era. 65 generations of humans, assuming 20 years per generation. Entire branches of civilization rising, flourishing, and transforming while the journey continues, relentless, toward the ringed world ahead. Languages would evolve beyond recognition. Political systems would be invented, perfected, and discarded. Technologies would advance from medieval metalworking to quantum computing and beyond. And through it all, the vehicle would continue its steady progress, 95 feet every second, 65 miles every hour, 1,560 miles every day, never stopping, never slowing. When Saturn reaches the far side of the Sun from Earth, at conjunction, the distance expands to approximately 1.6 billion kilometers or 994 million miles. This maximum separation requires 15,292,308 hours of travel, or 637,179 days, or 1,745 years, nearly 1,750 years, from the late Roman Empire to the present, from the time of Constantine to computers. Entire civilizations rising from nothing, achieving greatness, and falling to dust in the time it would take to drive this route. The scale defeats language. We have words for these durations, but no experiential reference. They exist in the realm of deep history, of cultural evolution, of geological patience. The average distance to Saturn, accounting for all orbital positions, settles at approximately 1.36 billion kilometers or 845 million miles. At highway speed, this requires 13 million hours or 541,667 days or 1,483 years, nearly 15 centuries on average to reach Saturn. From the fall of Rome to the space age, from the Tang dynasty to the internet. The journey time alone spans multiple epochs of human civilization, multiple waves of innovation and collapse, multiple transformations of how humans live and understand their world. The journey to Saturn would be profoundly isolating in ways even the Jupiter journey wasn't. After leaving Earth and spending centuries crossing the inner solar system, then more centuries reaching and passing Jupiter, you would enter a region where the sun's warmth becomes negligible. At Saturn's distance, sunlight is 90 times fainter than on Earth. High noon on Saturn provides about the same illumination as twilight on our world. The giant planet would gradually emerge from the darkness ahead, first as a point of light, then over decades and centuries as a visible disk, finally revealing its glorious rings after half a millennium or more of patient approach. Those rings would be worth the wait. Even from Earth, with good binoculars or a small telescope, Saturn's rings are visible, a stunning sight that stops first-time observers mid-breath. From space, approaching Saturn, the rings would be magnificent beyond description. You'd see the main divisions. The Cassini division, a gap 4,800 kilometers wide, separating the A and B rings. The Encke gap in the A ring. The crepe-like C ring inner region. You'd watch the rings change angle as Saturn moves through its orbit and your perspective shifts, sometimes presenting edge-on, when they nearly disappear from view despite their vast extent, because they're so thin, sometimes opening to show their full glory. The moons of Saturn would become visible as your centuries-long approach continued. Saturn has at least 146 known moons, ranging from tiny, irregular captured asteroids to substantial worlds. Titan, the largest, is bigger than Mercury and possesses a thick nitrogen atmosphere and lakes of liquid methane and ethane on its surface. It's the only moon in the solar system with a substantial atmosphere, and beneath its organic haze lies a world that might harbor exotic forms of life based on liquid methane rather than water. Enceladus, a smaller moon, has proven even more intriguing. The Cassini spacecraft discovered that Enceladus shoots geysers of water ice into space from its south polar region, indicating a liquid water ocean beneath its icy shell, heated by tidal flexing from Saturn's gravity. This makes Enceladus, like Europa at Jupiter, a prime candidate in the search for life beyond Earth. The Cassini mission, which orbited Saturn from 2004 to 2017, revealed Saturn's system in extraordinary detail. The spacecraft discovered new moons, new ring structures, watched storms develop and evolve in Saturn's atmosphere, including the massive hexagonal polar vortex, a six-sided jet stream at Saturn's north pole that remains unexplained by atmospheric dynamics. Cassini dropped the Huygens probe onto Titan's surface, revealing a landscape of ice, rocks, and liquid methane rivers. The mission transformed our understanding of Saturn from telescopic observations and brief Voyager flybys into a rich, detailed comprehension of a complex system of worlds. Your 13th century journey would give you time to watch this system evolve. Saturn's year is 29.5 Earth years, so over your journey, you'd see Saturn complete about 44 orbits, watching the ring angle change through multiple cycles, seeing seasonal variations in the planet's atmosphere. You'd watch the moons pursue their orbital dance, Titan completing an orbit every 16 days, Enceladus every 33 hours, tiny Prometheus and Pandora shepherding the F-ring particles into place. The system would cease being static images from books and become a living, evolving dance of gravity and motion. Saturn's atmosphere, like Jupiter's, shows banded structure, though less dramatically colored. The clouds are primarily ammonia ice crystals, tinted by trace amounts of other compounds. Wind speeds in Saturn's atmosphere can exceed 1,800 kilometers per hour, faster than Jupiter's jet streams despite Saturn's lower mass and energy output. The planet radiates more energy into space than it receives from the Sun, powered by gravitational contraction and differentiation of helium sinking toward the core. Saturn is still, in a sense, forming, its interior settling into configuration, releasing heat in the process. As your vehicle approached Saturn after its millennium-plus journey, you'd be arriving at a system that represents one of the pinnacles of natural beauty in the solar system. The rings alone justify the journey in aesthetic terms, but the wealth of moons, each a world unto itself, adds depth to the Saturn system that rewards study. You'd be reaching a realm where conventional weather gives way to exotic atmospheric phenomena, where moons harbor subsurface oceans and organic hazes, where ice dominates and temperature plunges to conditions that would flash freeze any terrestrial life instantly. But Saturn, for all its grandeur and distance, is not the end of the solar system. Beyond this ringed giant lie two more worlds, the ice giants Uranus and Neptune, orbiting in regions even more remote, where the sun provides barely more warmth than starlight, where orbital periods are measured in decades and centuries, where the journey times at highway speed will stretch into spans that dwarf even Saturn's 13 centuries. The road continues outward, into darkness and cold that represents the ultimate test of patience, the final frontiers of our planetary system. Beyond Saturn, the solar system undergoes a fundamental transformation. The giant planets give way to a different class of world. The ice giants, smaller than Jupiter and Saturn, but still massive compared to Earth, composed not primarily of hydrogen and helium, but of heavier elements called ices in astronomical terminology: water, methane, ammonia, compressed into exotic states by enormous pressure. The first of these ice giants is Uranus, seventh planet from the Sun, a world so distant that it wasn't discovered until 1781, when William Herschel spotted it through his telescope, initially thinking it was a comet before orbital calculations revealed its planetary nature. Uranus doubled the known size of the solar system overnight, pushing the boundaries of human awareness into a realm our ancestors couldn't have imagined. Uranus orbits at an average distance of 2.87 billion kilometers from the Sun, or 19.2 astronomical units. This places Uranus almost exactly twice as far from the Sun as Saturn, and nearly 4 times Jupiter's distance. At this remove, sunlight is already so faint that the Sun appears only slightly larger and brighter than other stars in the sky, providing illumination roughly 1,000th of what Earth receives. The temperature at Uranus's cloud tops hovers around -214 degrees Celsius, cold enough to freeze air solid if Earth's atmosphere could somehow be transported there. What makes Uranus unique among planets is its extreme axial tilt. While Earth tilts at 23.5 degrees, giving us seasons, and other planets have similar modest tilts, Uranus is tilted at 98 degrees, essentially lying on its side. This means Uranus's poles, at various points in its 84-year orbit, point almost directly at the Sun, creating bizarre seasonal patterns where each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. The cause of this unusual tilt remains uncertain, though most theories involve a catastrophic collision early in the solar system's history, perhaps with an Earth-sized body that knocked Uranus onto its side and scattered debris that eventually formed its system of moons and rings. When Earth and Uranus align at opposition, Uranus makes its closest approach to our planet. Due to the eccentricities of both orbits, this distance varies, but at typical closest approach, Uranus sits approximately 2.57 billion kilometers from Earth, or about 1.6 billion miles. At 65 miles per hour, covering 1.6 billion miles, requires 24,615,384 hours. That's 1,025,640 days, or 2,808 years. 2,808 years to reach Uranus at its nearest approach. 28 centuries of continuous travel. This is a timescale that reaches back beyond recorded history. 2,800 years ago, Homer was composing the Iliad and Odyssey, or perhaps these oral traditions were just beginning to crystallize into written form. The first Olympic Games were still decades in the future, but Rome hadn't been founded. The great philosophers of Greece, the Persian Empire, the Buddha, Confucius, all lay centuries ahead. If you had started driving toward Uranus then, maintaining highway speed through every moment of human civilization, since, through the rise of Rome, the birth of Christianity, the fall of empires, the Dark Ages, the Renaissance, the Enlightenment, the Industrial Revolution, the World Wars, the Space Age, the Digital Age, you would only now be arriving. 28 centuries, 140 generations. Every human who has ever lived could be placed in a line of direct descent from that ancient starting point to now, and it would barely fill the journey time to Uranus. When Uranus reaches the far side of the Sun from Earth, at conjunction, the distance expands to approximately 3.15 billion kilometers or 1.96 billion miles. This maximum separation requires 30,153,846 hours, or 1,256,410 days, or 3,443 years, over 3,400 years, from the Bronze Age to the Information Age, from the time of the ancient Hittites and Mycenaeans to modern democracies and space stations. Entire systems of writing would be invented, flourish, and become archaeological curiosities over such a span. Religions would arise, spread across continents, schism into sects, and evolve beyond recognition. Technologies would advance from bronze tools to quantum computers. And through it all, the vehicle would push forward, mile after relentless mile, into the outer darkness. The average distance to Uranus, accounting for all orbital configurations, settles at approximately 2.7 billion kilometers or 1.68 billion miles. At highway speed, this requires 25,846,154 hours, or 1,076,923 days, or 2,950 years. Nearly 3,000 years on average, from Homer to Hubble, from bronze to bytes. The span encompasses the entire arc of Western civilization, and then some. This is no longer a journey. It's a geological epoch, a cultural transformation, a period against which we measure civilizations rather than lives. The journey to Uranus would take you through unimaginable isolation. After spending over 1,000 years reaching Saturn, you would continue outward for another 1,500 to 2,500 years, depending on orbital positions. The Sun would shrink further, becoming merely the brightest star rather than the dominating presence it is from the inner system. The solar wind, that stream of charged particles flowing outward from the Sun, would have weakened to a whisper. You'd be approaching the outer reaches of the heliosphere, that bubble of solar influence beyond which interstellar space begins. Uranus would gradually reveal itself over the centuries. First appearing as a tiny disk, barely more than a point, it would slowly grow. The planet's color would become apparent. A pale blue-green, caused by methane in its atmosphere, absorbing red light and reflecting blue and green wavelengths back into space. Unlike Jupiter and Saturn, with their obvious banded structure and dramatic storms, Uranus appears nearly featureless at visible wavelengths, a serene sphere of cyan rotating every 17 hours. But this placid appearance masks a strange interior where water, methane, and ammonia exist in a sort of hot ice state, compressed by immense pressure into a solid liquid hybrid that flows like a very thick liquid while having properties of a solid. Voyager 2, the only spacecraft to visit Uranus, flew past the planet in January 1986, providing our only close-up observations. The probe discovered 10 new moons, revealed the complex structure of Uranus's faint ring system, measured the planet's magnetic field, which is tilted 60 degrees from the rotation axis and offset from the center, suggesting unusual dynamics in the conducting region that generates it, and captured images that showed a few faint clouds in an otherwise uniform atmosphere. Recent observations from Earth-based telescopes and Hubble have shown that Uranus experiences seasons with increased storm activity as the planet moves through its peculiar seasonal cycle. But overall, Uranus remains one of the least understood planets in our solar system. The moons of Uranus are named after characters from Shakespeare and Alexander Pope, a departure from the mythological naming convention used for other planets' satellites. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, orbit in the plane of Uranus's equator, meaning they're tilted with the planet, creating an unusual configuration where the moon system sometimes appears as concentric rings around Uranus from Earth's perspective, and other times spreads out like a bullseye target. Miranda, the smallest of the major moons, shows some of the most dramatic terrain in the solar system, with cliffs 15 kilometers high and a patchwork surface suggesting a violent past, possibly involving shattering and reassembly after a major collision. Your multi-millennium journey would encompass dozens of Uranian years, watching the bizarre seasonal cycle play out repeatedly. You'd see each pole take its turn pointing toward or away from the sun, creating conditions where half the planet experiences decades of daylight, while the other half freezes in darkness, then gradually reversing. You'd watch the moons trace their orbits, sometimes edge-on from your perspective, other times spread in a circle. The rings, though faint, would become visible as you approached. 13 distinct rings composed of dark particles, possibly organic compounds darkened by radiation, quite different from Saturn's bright ice rings. Uranus challenges our understanding of planetary formation. Its methane atmosphere, its rocky icy interior, its bizarre tilt and offset magnetic field, all suggest a complex history that models struggle to fully explain. The planet seems to retain less heat than expected, radiating barely more energy than it receives from the Sun, unlike Jupiter and Saturn, which have substantial internal heat sources. Why is Uranus so cold internally? What process depleted its heat, or prevented it from developing a strong heat source in the first place? These questions await future missions, distant prospects given the journey times even for our fastest spacecraft. Voyager 2 took 9 years to reach Uranus, and no mission is currently funded or planned to return, though proposals circulate in the planetary science community. As your vehicle finally approached Uranus after 28 centuries, or 34 centuries, or 3,000 years depending on alignment, you'd be arriving at one of the solar system's great mysteries, a world that looks serene but hides complexity beneath its placid clouds. You'd be reaching a place where human presence, even robotic, has barely touched, where vast amounts of basic science remain to be done. And yet, for all the remoteness and strangeness of Uranus, one final world remains ahead. The last planet, the final outpost before the solar system gives way to the realm of comets and the interstellar void beyond. Neptune beckons deeper still into the darkness, requiring a patience that transcends civilizations and approaches geological timescales. The highway continues, one last push into the ultimate depths of our planetary neighborhood. At the outermost edge of the planetary system, 30 times further from the Sun than Earth, orbits Neptune, the final major world in our solar family. This deep blue giant, twin to Uranus in size but distinct in character, represents the absolute frontier of planetary space. Beyond Neptune lies only the realm of dwarf planets like Pluto, the scattered disk of icy bodies, the Kuiper Belt, and eventually the Oort cloud, that distant sphere of comets that marks the true edge of the Sun's gravitational dominion. Neptune stands as the last sentinel, the final port of call before the highway gives way to interstellar emptiness. Neptune wasn't discovered through observation, but through mathematics. By the early 1800s, astronomers had noticed that Uranus didn't quite follow its predicted orbit. Something was pulling at it gravitationally. In 1846, Urbain Le Verrier in France and John Couch Adams in England independently calculated where an unknown planet would need to be to explain Uranus's orbital perturbations. When Johann Galle in Berlin pointed his telescope at Le Verrier's predicted position, there was Neptune, exactly where mathematics said it should be. This triumph of theoretical astronomy extended humanity's reach to a world so distant that even detecting it was an achievement, let alone imagining traveling there. Neptune orbits the Sun at an average distance of 4.5 billion kilometers, or 30.07 astronomical units. This immense distance places Neptune 30 times farther from the Sun than Earth, in a region where sunlight provides barely more warmth than starlight, where the solar disk appears no larger than a bright star, where temperatures plunge to negative 214 degrees Celsius at the cloud tops. At this distance, the Sun's gravitational hold, while still dominant, has weakened to the point where Neptune takes 165 Earth years to complete a single orbit, meaning that since its discovery in 1846, Neptune has completed only a single orbit plus a handful of years as of now. When Neptune reaches opposition, positioning itself on the opposite side of Earth from the Sun, it makes its closest approach to our world. At opposition, Neptune sits roughly 2.7 billion miles or 4.3 billion kilometers from Earth, about 28.9 astronomical units, though this varies slightly depending on where each planet is in its elliptical orbit. This is Neptune's nearest approach, the alignment that brings the distant ice giant as close as it ever gets to our world. At 65 miles per hour, covering 2.7 billion miles, requires 41,538,461 hours of continuous driving. That's 1,730,768 days, which translates to 4,742 years. 4,742 years to reach Neptune at its closest approach. Let that duration settle into your consciousness. 4,742 years, nearly 5 millennia, from the construction of the pyramids at Giza to the present day, from the dawn of written history in Mesopotamia to spacecraft and satellites, from bronze tools to quantum computers, from the earliest civilizations rising in river valleys to global technological society. 237 generations of humans, assuming 20 years per generation. Every pharaoh who ruled Egypt, every emperor of Rome and China, every kingdom that rose and fell in Europe, Asia, Africa, the Americas. All of recorded human history would fit within this journey time, and you would still be driving year after year, century after century, millennium after millennium, watching the distant blue speck of Neptune grow imperceptibly larger. When Neptune swings to the far side of the Sun from Earth, reaching conjunction, the distance expands further. At maximum separation, Neptune can lie approximately 4.7 billion kilometers or 2.9 billion miles from Earth. At highway speed, this maximum distance requires 44,615,384 hours or 1,858,974 days or 5,092 years. Over 5,000 years. From the first cities in Mesopotamia to the space age. From the invention of the wheel to interplanetary spacecraft. From stone temples to glass towers. The entire span of civilization, every war, every peace, every discovery, every artwork, every philosophy, compressed into the journey time to Neptune at its most distant. The average distance to Neptune, accounting for all possible orbital positions, settles at approximately 4.5 billion kilometers or 2.8 billion miles, roughly 30 AU. This average distance requires 43,076,923 hours of travel time, or 1,794,871 days, or 4,917 years, nearly 5,000 years on average. From the Bronze Age to the Digital Age. This is a timescale that encompasses the entire written record of humanity. Everything we call history, every named person who ever lived, every dated event, every monument and document exists within a span shorter than the average journey time to Neptune at highway speed. These numbers defy comprehension. We simply have no experiential framework for durations measured in millennia. A human lifetime, even a long one, is less than 2% of the journey time to Neptune. The entire United States has existed for less than 5% of this duration. The scientific revolution, from Galileo to the present, covers only about 8% of the trip. We are discussing timescales that belong to species evolution, to continental drift, to the slow accumulation of sedimentary rock, not to anything a conscious being could experience or even meaningfully imagine experiencing. Imagine undertaking this journey, impossible as that is. You leave Earth, accelerating to 65 miles per hour and maintaining that speed. The first century passes. You're still barely out of the inner solar system. The first millennium passes. You've covered perhaps 20% of the distance. Entire civilizations on Earth rise, flourish, transform, and collapse. Languages evolve, scripts are invented, philosophies flourish and fade. The second millennium passes. You're perhaps halfway to Neptune now, though distances in space can be deceptive and the halfway point in miles doesn't match the halfway point in time due to varying orbital positions. The third millennium. The fourth. You've been traveling longer than recorded history existed when you started. Earth, if you could still receive signals from it, would be unrecognizable, transformed by technologies and societies you couldn't have imagined at departure. And finally, after 5,000 years, Neptune would begin to resolve as more than just a point of light. That pale blue disk, tinted by methane absorption in its atmosphere, would gradually grow. The planet's features would emerge: dynamic storm systems with winds approaching 600 meters per second, faster than the speed of sound, driven by mysterious internal heat sources. The Great Dark Spot and other storm features would rotate into and out of view as Neptune spins every 16 hours. The planet's bizarre ring system, with its characteristic arcs where material clumps mysteriously, would become visible. And Triton, Neptune's largest moon, that strange world captured from the Kuiper Belt and forced into retrograde orbit, would appear as a separate disk orbiting opposite to Neptune's rotation. Triton remains one of the most intriguing moons in the solar system. Despite surface temperatures around -391 degrees Fahrenheit, Voyager 2 discovered geysers erupting from its surface, shooting nitrogen ice 5 miles high into Triton's tenuous atmosphere. This geological activity on such a frigid world hints at tidal heating from Neptune's gravity, the same mechanism that keeps Europa and Enceladus geologically active. Triton might harbor a subsurface ocean beneath its frozen shell, another candidate in the solar system's growing list of potentially habitable environments, though habitable at such distances and temperatures requires redefining what life might be. Neptune itself challenges our understanding of planetary science. Despite being more than 30 times farther from the Sun than Earth and receiving 900 times less sunlight, Neptune possesses the windiest weather in the solar system, with gusts 3 times stronger than Jupiter's, which sits much closer to the Sun's warmth. Where does Neptune get the energy to drive such ferocious atmospheric activity? The planet radiates more than twice as much energy into space as it receives from the Sun, indicating a substantial internal heat source, likely from gravitational contraction and the differentiation of heavier elements sinking toward the core. Neptune is still evolving, still settling into its final configuration billions of years after formation. The planet's composition sets it apart from the gas giants Jupiter and Saturn. Neptune and Uranus are called ice giants because, while still enormous, they contain far less hydrogen and helium than their larger siblings. Instead, their interiors are dominated by ices, in astronomical terminology, meaning water, methane, and ammonia. Though at the temperatures and pressures inside these planets, these substances exist in exotic states far removed from anything we'd call ice. They form superhot, superdense fluids, possibly with separated layers, maybe containing exotic compounds like superionic water, where oxygen atoms form a crystalline lattice while hydrogen atoms flow freely through it like a liquid metal. We don't know for certain. Voyager 2 remains the only spacecraft to have visited Neptune, flying past in 1989 after a 12-year journey and providing our only close-up data on this system. That Voyager 2 mission, covering Neptune's distance in 12 years instead of 5,000, used gravitational assists from Jupiter and Saturn to build up velocity, traveling at speeds approaching 40,000 miles per hour at various points in its trajectory. Even so, 12 years represents a substantial chunk of human lifespan, a mission that required patience and long-term planning. Scientists who worked on Voyager's initial design saw their children grow up, start careers, and have children of their own before the spacecraft reached Neptune. And that was the fast route. Our highway speed journey, 5,000 years in duration, is so far beyond human timescales that it ceases to be a journey and becomes something else entirely. A metaphor for isolation, a meditation on scale, a reminder that the solar system, for all our exploration, remains fundamentally alien to human accessibility at ordinary speeds. As your vehicle finally approached Neptune after its epic 5-millennium journey, you'd be arriving at the edge of the planetary realm. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including Pluto and other dwarf planets, then the scattered disk, then eventually the Oort cloud, that vast sphere of comets marking the Sun's true gravitational boundary, extending perhaps 2 light-years into space. But Neptune represents the last of the 8 major planets, the final world massive enough to have cleared its orbital path and achieved the dynamical dominance that defines planethood under current definitions. Neptune's discovery, predicted mathematically before being observed, represented a triumph of human intellect, proof that Newton's laws of gravity and motion could be trusted even at distances where observation was difficult. Leverrier and Adams, working independently with nothing but mathematics and the observed perturbations in Uranus's orbit, calculated where an unknown planet must exist. When Galilei pointed his telescope at that position and found Neptune almost exactly where predicted, it validated 2 centuries of theoretical development and announced that human understanding had reached across the solar system, that we could comprehend what we couldn't yet see. Our 5,000-year hypothetical journey to Neptune ends at this world of mystery and beauty. This frozen giant whipped by supersonic winds, orbited by a captured moon shooting geysers into space, ringed by clumps of debris that shouldn't exist according to simple orbital mechanics, but do anyway. We arrive at a place that represents both the culmination of our outward push and the beginning of truly deep space, where the planets give way to smaller bodies and the sun's dominion fades toward the interstellar realm. The journey has taken longer than human civilization has existed. It has spanned timescales we can barely name. And it reminds us, with crushing clarity, that space is not empty, but full of distance, full of time, full of separation that defeats any casual attempt to cross it. Neptune waits at the end of the longest highway, the ultimate destination in our cosmic road trip, 5,000 years away at the speeds we know from Earth. Now that we've traveled, in imagination, to each planet in our solar system at highway speed, let's step back and examine what these numbers actually mean when placed side by side. The journey times we've calculated span from decades to millennia, from substantial portions of a single human life to periods that encompass the entire history of human civilization. Placing these durations in comparison reveals not just the distances between worlds, but something deeper about the structure and scale of our solar neighborhood and our place within it. Mercury, at its closest approach, requires 84 years of continuous travel. Venus, at closest approach, takes 43 years. Mars needs 61 years during a favorable opposition. These inner planets, the rocky worlds that share the inner solar system with Earth, are accessible within a long human lifetime when orbital geometry cooperates. They're distant, yes, requiring generations of patience by human standards of daily travel, but not impossible to conceive. A person born at the start of the journey to Venus might live to see its completion, though they'd be elderly. The trip to Mercury or Mars would likely outlive any single traveler, but not by an order of magnitude. These are human-scale times, stretched to their absolute limits, but still comprehensible. But then we cross into the realm of the giants, and the numbers transform. Jupiter, even at its closest approach, requires 644 years. Saturn demands 1,310 years at its nearest. These are no longer lifetimes, but dynasties. No longer biographies, but histories. The journey to Jupiter spans from the late medieval period to now, from the Black Death to the International Space Station. The trip to Saturn covers the entire period from the Crusades to the present, from Gothic cathedrals to genetic engineering. We're discussing timescales measured in centuries, periods during which languages evolve, empires rise and crumble, entire systems of thought emerge and are superseded. And then we push further still to the ice giants at the solar system's edge, and the numbers explode into the realm of civilizational time. Uranus, at closest approach, lies 2,808 years away at highway speed. Neptune requires 4,742 years. These aren't journeys, they're epochs. The voyage to Uranus covers the entire span from Homer to the present, from the first Olympic Games to the Mars rovers. The trip to Neptune encompasses everything from the construction of Stonehenge to supersonic aircraft, from the invention of writing to artificial intelligence, from the first cities to space telescopes. Every person whose name appears in a history book, every dated event we can point to, occurs within a time frame shorter than the journey to Neptune. Let's look at the average. Distances, which smooth out the orbital variations and give us a representative number for each planet. Mercury averages 108 years away. Venus takes 73 years on average. Mars requires 245 years typically. Jupiter sits 685 years away on average. Saturn lies 1,483 years distant. Uranus averages 2,950 years. Neptune requires 4,917 years. The pattern is clear. Distances increase not linearly, but in expanding jumps as we move outward, each planet requiring exponentially more patience than the last. If we arrange the planets by their average journey time at highway speed, we get a hierarchy of accessibility that might surprise those who think only in terms of orbital position. Venus, despite being the second planet from the Sun, is actually the quickest average trip at 73 years, thanks to its orbit being close to Earth's. Mercury, though closer to the Sun, averages 108 years because its orbit takes it far from Earth at times. Mars, the red planet of exploration dreams, averages 245 years, making it more distant on average than either Mercury or Venus. This counterintuitive result explains why Mars missions require careful timing to launch during favorable oppositions. The outer planets then cascade into ever greater durations. Jupiter, Saturn, Uranus, Neptune, each multiplying the journey time significantly. Consider what you could accomplish on Earth in these time scans. In 43 years, the shortest planetary journey, you could complete a career, raise a family, watch grandchildren be born. In 84 years, you could witness the entire adult life of another human, from graduation to retirement. In 644 years, the trip to Jupiter, you could watch the entire Renaissance unfold, from Dante to Newton, from medieval scholarship to the birth of modern science. In 5,000 years, the Neptune journey, you could observe the entire progression from primitive agriculture to space exploration, from copper tools to quantum computers, from oral tradition to global internet. The journey times also reveal something about why we've explored the solar system in the order we have. We've sent successful missions to every planet, but the frequency and detail of our exploration correlates inversely with journey time. Mars has been visited by dozens of landers and rovers because the journey, while taking months for spacecraft, is achievable within mission lifetimes and career spans. Jupiter and Saturn have been studied by multiple flybys and orbiters because, while requiring years to reach, the missions can still be completed within a couple decades. Uranus and Neptune have each received only a single flyby, Voyager 2, because the investment required to reach them strains even our accelerated spacecraft timelines. No missions are currently funded to return to either ice giant, though scientists have proposed concepts. The highway speed journey times, multiplied by hundreds to represent spacecraft velocities, still result in mission durations measured in years or decades, requiring sustained funding and long-term institutional commitment that's difficult to maintain. These comparisons also highlight the profound isolation of Earth. Our nearest planetary neighbors, under optimal conditions, lie decades away at speeds we use for terrestrial travel. Our more distant siblings require centuries or millennia. In the cosmic sense, we're alone on Earth, separated from even our closest companions by gulfs of space that translate into gulfs of time so vast they challenge human patience and imagination. The phrase, astronomical distances, takes on visceral meaning when we convert those distances into journey times at speeds we know from everyday experience. Suddenly, the abstract becomes concrete. 10 billion kilometers isn't just a large number, it's 5,000 years of your life, or 5,000 years of anybody's life spent traveling. The odometer readings for these journeys are equally staggering. The trip to Venus, shortest on average, would accumulate roughly 639 million miles. Mercury averages 940 million miles of travel. Mars requires 2.1 billion miles. Jupiter's journey racks up 5.9 billion miles. Saturn demands 11.7 billion miles. Uranus requires 24 billion miles of driving. Neptune pushes the odometer to 44 billion miles. These are numbers beyond anything mechanical devices could record. They're numbers that exist only in astronomical context, distances that have no meaning in terrestrial terms. You could drive around Earth's equator 1,000,000 times and still not cover the distance to Neptune. What about fuel? If our hypothetical vehicle achieved a modest 30 miles per gallon, typical for highway driving, the journey to Neptune would consume approximately 1.47 billion gallons of gasoline. If fuel cost $3 per gallon, you'd spend $4.4 billion on gas alone, not accounting for inflation over 5,000 years, not including any maintenance, not considering that your vehicle would need to be replaced millions of times as components wore out. The economics become absurd, but they illustrate the raw energy required to traverse these distances. Actual spacecraft use far more efficient propulsion relative to their mass, but even so, every kilogram of spacecraft sent to the outer solar system represents enormous investments of fuel and energy just to achieve the velocities needed to make the journey in years rather than millennia. Time dilation, a relativistic effect, wouldn't factor into our highway speed journey. At 65 miles per hour, we're moving at about 0.0001% the speed of light, far too slow for relativistic effects to be measurable. But if we could somehow achieve velocities approaching light speed, time would compress for the traveler while ages passed on Earth, creating the famous twin paradox where a space traveler returns younger than their stay-at-home sibling. At highway speeds, though, time ticks forward at the same rate for the traveler and for those on Earth. 5,000 years pass for both. There's no shortcut, no relativistic compression to make the journey easier. Just the patient accumulation of seconds into minutes, into hours, into days, into years, into centuries, into millennia. The comparison of these journey times also raises philosophical questions about accessibility and value. Is Mars more interesting than Neptune simply because it's more accessible? Do we prioritize Mercury and Venus in our imagination because they're reachable within longer lifetimes? Or does the very remoteness of Uranus and Neptune add to their mystique, their alien quality enhanced by the impossibility of casual visits? Throughout history, distant lands have held special appeal precisely because they were difficult to reach. The Silk Road, the spice routes, the voyages of exploration sought out remote destinations, and the difficulty of the journey added value to what was found. Perhaps Neptune's 5,000-year highway journey, impossible in practice but imaginable in thought, adds to rather than detracts from its fascination. What these numbers ultimately reveal is that space, for all our technological progress, remains fundamentally foreign to human scales of time and distance. We are creatures adapted to a world where cross a continent in days, circle the globe in hours via aircraft, and measure our lives in decades. The solar system operates on different scales entirely. Distances measure in billions of miles, journeys measure in centuries or millennia, orbits measure in decades or centuries for the outer planets. We've built technologies that let us project ourselves across these distances much faster than highway speed, but even our fastest spacecraft require years to reach the outer system and decades to exit the heliosphere entirely. Voyager 1, launched in 1977, only recently crossed into interstellar space after more than 40 years of travel, and it's moving at 38,000 miles per hour, almost 600 times our highway speed. The arithmetic of these cosmic journeys is the arithmetic of patience, of deep time, of scales that transcend individual human experience. It's the arithmetic of a universe built on a vastness that makes our planet, for all its diversity and beauty, a tiny island in an ocean of space. The highway to the planets is long, measured not in exit numbers but in generations and ages, and the journey times remind us that while we can imagine traveling these distances, while we can calculate the numbers and contemplate the durations, we are fundamentally bound to our world by time as much as by space, by the length of our lives as much as by the distances between worlds. The cosmos is accessible to our minds, to our mathematics, to our robot emissaries, but the highway journey shows us that, in terms of human-scale travel, the planets remain as distant as they were to the ancients, transformed from mysterious lights into known worlds, but no closer in the lived experience of crossing space 1 mile at a time. Throughout this journey, calculating the years and decades and centuries required to reach each planet at highway speed, a deeper truth has emerged beneath the numbers. The solar system, our home neighborhood in space, is almost incomprehensibly vast when measured in human terms. We use words like nearby for Venus or Mars, distant for Neptune, but these are relative terms that obscure the absolute scale of separation. In truth, even our nearest planetary neighbors are isolated from us by gulfs of space that translate into gulfs of time measured in lifetimes. And our farthest siblings lie across chasms of 5 millennia, separating us not just by distance, but by the entire span of recorded history. This loneliness, this isolation, is one of the fundamental facts of our existence. Earth is alone in space. Yes, we orbit the Sun along with 7 other major planets, dozens of dwarf planets, hundreds of moons, and countless asteroids and comets. But the spaces between these worlds are so vast, so empty, that each body effectively exists in its own bubble of isolation. Light, traveling at the ultimate speed limit of the universe, takes minutes to hours to cross the distances between planets. Radio signals moving at light speed face the same delays. A conversation with a Mars rover involves waiting 20 minutes or more for each exchange, the radio waves crawling across space at 186,000 miles per second, yet still requiring significant time to traverse the gap. A conversation with a probe at Neptune would involve waits of 8 hours or more for each round trip, making real-time communication impossible. At highway speeds, these light-minute and light-hour distances explode into durations measured in human generations and historical epochs. We've spent this entire journey calculating what it would mean to drive to each planet at 65 miles per hour, and the answer, repeatedly, has been, it would take longer than we can meaningfully imagine, longer than lives, longer than dynasties, longer than civilizations. The highway journey reveals what the raw numbers in astronomical texts sometimes obscure. That space is not just big, it's hostile to crossing at scales we know from daily life. It defeats patience, it defeats endurance. It requires either technologies that enable velocities hundreds of times faster than highway speed, or it requires patience measured in geological time, or it simply cannot be done. And yet, despite this crushing isolation, despite the centuries and millennia that separate world from world we have explored, we've sent spacecraft to every planet in the solar system. We've orbited several. We've landed on a few. We've brought samples back from the Moon, and soon from Mars. We've achieved this not by finding shortcuts through space, not by discovering wormholes or warp drives, but by patient application of physics and engineering. We build machines that can withstand years or decades in the vacuum of space. We calculate trajectories that use gravitational assists to build up velocity, borrowing momentum from one planet to reach the next. We design systems robust enough to function after years of travel, still capable of carrying out their missions when they arrive at destinations so distant that radio commands from Earth take hours to reach them. The Voyager spacecraft, both 1 and 2, are perhaps the ultimate expression of this patient exploration. Launched in 1977, they visited Jupiter and Saturn, with Voyager 2 continuing to Uranus and Neptune. These missions required years of travel even at spacecraft velocities, and decades later, both Voyagers continue to operate, now in interstellar space beyond the heliopause, sending back data on the boundary between solar and interstellar realms. The scientists who designed these spacecraft were young or middle-aged at launch. Many have retired or passed away. The Voyagers outlived their designers' careers and will likely continue operating until some critical system finally fails, perhaps another decade from now. These machines, traveling at speeds we calculated, would reduce Neptune's journey from 5,000 years to 12 years, represent humanity's farthest reach, our most distant ambassadors, carrying golden records with sounds and images of Earth in case some future intelligence encounters them. What drives this exploration despite the distances? Partly, it's simple curiosity, the human desire to know what's over the next hill, around the next corner, orbiting the next planet. We're a curious species, driven to explore even when exploration requires decades of our lives or centuries of our civilization's effort. Partly it's practical. Understanding the solar system helps us understand Earth's history, climate, and future. The planets are natural laboratories where we can observe processes, frozen, absent, or at different scales than on Earth. Studying Venus's runaway greenhouse effect informs our understanding of climate change. Examining Mars's lost water helps us understand how planets evolve. Observing Jupiter's magnetosphere reveals plasma physics in action on scales impossible to replicate in laboratories. But partly, perhaps primarily, we explore because the isolation itself demands it. Being alone on Earth, separated from all other worlds by vast distances, creates a yearning to reach out, to connect, to bridge the gaps however we can. If we could drive to Mars, we would. If we could visit Neptune on a highway journey, someone would attempt it despite the millennia required. Since we can't, we send proxies, robots, and spacecraft that go where we cannot, that see what we cannot see, that transform the isolation into a different kind of connection. When Curiosity roves across Mars, it's humanity exploring vicariously. When Juno orbits Jupiter, it's humanity investigating a giant world. When New Horizons flew past Pluto, it was humanity reaching the edge of the planetary system, peering into the Kuiper Belt, pushing back the frontier of the unknown. The highway journey we've imagined throughout this script serves a purpose beyond simple calculation. By translating astronomical distances into familiar speeds and units of time, we've made the vastness of space visceral. Saying Neptune is 4.5 billion kilometers away communicates information but not feeling. Saying Neptune is 5,000 years away at highway speed communicates the same information but adds emotional weight. 5,000 years is history. It's everything we know about human civilization. It's the span from the first cities to space stations. Framing Neptune's distance in these terms transforms it from an abstract number into something we can feel in our bones, a duration that crushes us with its magnitude, that forces us to confront the genuine isolation of our world. This isolation also reframes our relationship with Earth. When you truly internalize that Venus, our nearest neighbor, lies 43 years away at highway speed, and that every other planet is farther still, Earth's uniqueness becomes undeniable. We are not just alone in the cosmic sense of no other intelligent life nearby. We are alone in the practical sense of being separated from even our nearest neighbors by distances that defeat easy crossing. Earth is an island, maybe the only inhabited island in a vast ocean of space, and the nearest potentially habitable shores lie decades or centuries or millennia away at any speed we could practically achieve. This makes Earth precious beyond measure. We cannot leave it casually. We cannot escape to other worlds if we damage this one. We are bound here, at least for the foreseeable future, residents of the only world in the solar system capable of supporting human life without extensive technological intervention. The poetry in all this lies in the juxtaposition of scale and achievement. The distances are crushing, but we've crossed them anyway, with machines, if not with bodies. The journey times at human speeds are measured in epochs, but we've compressed those epochs into years and decades through clever engineering and patient mission planning. The isolation is absolute, but we've refused to accept it as final, reaching out repeatedly with spacecraft and signals, studying and documenting our planetary siblings despite the challenges. There's something deeply human in this refusal to be limited by distance, in this insistence on exploring even when. Exploration requires decades of investment and centuries of accumulated knowledge. As we've traveled this imaginary highway from Mercury to Neptune, accumulating centuries and millennia of journey time, we've also been traveling through a landscape of human aspiration. Each planet represents not just a physical destination, but a milestone in our understanding. Mercury, hot and cratered, shows us worlds can be, teaches us about tidal locking and proximity to the sun. Venus, shrouded and hellish, warns us about greenhouse effects and lost habitability. Mars, cold and dry, hints at past water and possible past or present life, calling us forward toward boots on its surface. Jupiter and Saturn, the giants, reveal planetary formation on a grand scale, show us magnetic fields and atmospheric dynamics that dwarf anything terrestrial. Uranus and Neptune, tilted and windy, demonstrate that planetary systems contain variety we're only beginning to understand. Each world teaches us something, and the accumulated lessons form our modern understanding of how planets form, evolve, and change. The highway speeds we've used, 65 miles per hour, are speeds we know from our lives. We've all driven at this pace, felt the motion, watched the miles accumulate on long road trips. By using this familiar speed as our standard, we've grounded the cosmic in the everyday. This creates a bridge between our lived experience and the astronomical realm, making the vast suddenly relatable. Yes, Neptune is unimaginably far away, but we can imagine driving for 5,000 years. It would take forever, more than forever, longer than civilization has existed, but we can conceive of it. We can picture the odometer clicking forward, the painted lines blurring past, the slow accumulation of miles and years and centuries. This bridge, between the known and the vast, is where understanding lives. And perhaps that's the ultimate lesson of our cosmic highway journey. The universe is vast beyond human scales, but it's not beyond human understanding. We can calculate these distances, imagine these journeys, comprehend the isolation even if we can't directly experience travel across such spans. We can build machines that go where we cannot, extending our reach across billions of miles. We can use mathematics and physics to predict what we'll find before we arrive, then send spacecraft to confirm or surprise us. We can take the incomprehensible and make it comprehensible, not by shrinking it down, but by building up our capacity to grasp it through calculation, visualization, and patient study. The loneliness of distance, the epochs required to cross space at human speeds, the crushing vastness of the solar system, these aren't barriers to exploration. They're challenges that demand clever solutions. They're problems that require cooperation across decades and nations. They're obstacles that make the achievements, when they come, all the more remarkable. When Voyager 2 reached Neptune after 12 years of travel, it was a triumph not despite the distance, but because of it. The very difficulty made the accomplishment meaningful. And our highway journey, impossible in practice but illuminating in concept, serves the same purpose. It makes the distances real, makes the isolation visceral, makes the achievement of actual exploration more impressive by contrast. As we prepare to conclude our journey, having driven in imagination from the scorched nearness of Mercury to the frozen edge of Neptune, having accumulated enough imaginary miles to wrap the Earth tens of thousands of times, having spent lifetimes and dynasties and civilizations crossing the solar system at highway speed, we carry with us a new appreciation for both the vastness of space and the remarkable nature of exploration. The highway to the planets is long, far longer than any road on Earth, longer than any journey humans have ever undertaken physically. But we've traveled it mentally, and in doing so, we've transformed abstract astronomical distances into felt durations, into human-scale time that helps us grasp what the numbers alone could not convey. The cosmos is vast, but our capacity to understand and explore it, to reach across the gulfs of space with both machines and imagination, is equally vast in its own way. And that, perhaps, is the real poetry of exploration. Not that we can cross these distances easily, but that we refuse to let them stop us from trying. We've reached the end of our impossible road trip, having traversed in imagination the entire span of the solar system at a speed we know from everyday life. From Mercury, requiring a human lifetime to reach at closest approach, through Venus and Mars, accessible within long lifetimes or a few generations, past Jupiter and Saturn, demanding centuries and over a millennium, to Uranus and Neptune lying at the far side of human history, we've accumulated journey times that span from decades to 5 millennia. We've calculated distances in billions of miles, watched odometers roll over into numbers that lose meaning, contemplated spans of time that encompass the rise and fall of civilizations. And through it all, one truth has emerged with crystal clarity. The solar system, our immediate neighborhood in the cosmos, is vast beyond anything we encounter in daily life. 65 miles per hour, a comfortable highway cruising speed, reveals itself as hopelessly slow when projected into space. At this pace, even our nearest planetary neighbors lie decades away. The outer solar system retreats into timescales measured in millennia, distances that would consume not just individual lives, but the entire span of recorded human history. The highway we've imagined, connecting Earth to each planet in turn, stretched across distances that would require fuel measured in billions of gallons, maintenance that would rebuild the vehicle millions of times, patience that would exhaust species rather than individuals. This highway cannot exist. The journey cannot be taken as we've described it. And yet, the thought experiment serves its purpose. It transforms abstract astronomical distances into felt durations, gives us a visceral sense of the isolation that surrounds our world. What do these numbers teach us? First, they teach humility. We are small, living on a small world in a vast system, separated from even our nearest neighbors by gulfs that dwarf any terrestrial distance. The oceans that once seemed impossibly wide to ancient mariners are nothing compared to the spaces between planets. The continents that took months to cross in the age of sail are trivial next to the decades or centuries required to reach other worlds at speeds we know from Earth. Our planet, for all its size in our eyes, is a mote of dust in the solar system, and the solar system itself is a mote of dust in the galaxy, and the galaxy is a mote of dust in the universe. This nested hierarchy of scales, each layer dwarfing the previous, puts human existence into perspective that's simultaneously humbling and awe-inspiring. Second, these numbers teach us appreciation for what we've accomplished. When you truly grasp that Neptune lies 5,000 years away at highway speed, the fact that Voyager 2 reached it in 12 years becomes breathtaking. That 12-year journey required accelerating to speeds hundreds of times faster than our highway pace, maintaining those speeds through the vacuum of space, using gravitational assists from giant planets to build up velocity, and keeping all systems functional across more than a decade of exposure to radiation, micrometeorite impacts, and the cold of deep space. Every spacecraft that reaches any planet represents a triumph of engineering, physics, and patient mission planning. The Cassini mission, which orbited Saturn for 13 years, the Mars rovers that have driven across Martian terrain for years, the Dawn spacecraft that visited 2 asteroids, each of these missions compressed what would be civilizational journeys at highway speed into accomplishments measurable within careers and decades. This is extraordinary. Third, these numbers teach us the uniqueness of Earth. When every other world lies decades or centuries or millennia away at any practical speed, when traveling to even the nearest planets would consume lifetimes, the fact that we live on a world with breathable air, liquid water, moderate temperatures, and abundant life becomes more remarkable. Earth isn't just our home. It's our only accessible home, likely for centuries to come. The dream of Mars colonies, of orbital habitats, of spreading humanity across the solar system must contend with the reality of these distances. Even Mars, the most hospitable planet beyond Earth, lies months away for spacecraft and decades away at speeds we use terrestrially. Establishing permanent presence beyond Earth will require technologies, resources, and commitments that exceed anything we've yet attempted. The highway journey times remind us that space colonization isn't just technologically challenging, it's existentially challenging, requiring patience and investment that spans generations. Fourth, these numbers teach us about time itself. We measure our lives in years and decades. We measure history in centuries. We measure geology and evolution in millions of years. The highway journey times to the planets fall into that middle range where they're too long for individual experience, but too short for geological processes. They're civilizational times, the spans across which human societies change, languages evolve, and knowledge accumulates. By framing planetary distances in these terms, we create a new way of thinking about cosmic space. It's not empty void to be ignored. Its duration, filled with time, representing a barrier made not of physical obstacles, but of patience required, of the years that would tick past as the journey continued. This temporal dimension of distance is often overlooked in favor of spatial measurements, but it's equally important for understanding our relationship with the cosmos. The journey we've imagined, driving from Earth to Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune at 65 miles per hour cannot be undertaken in reality. We have no way to build a road through space. Our vehicles cannot survive in vacuum. We couldn't carry enough fuel. No human or team of humans or civilization could maintain the journey across the centuries or millennia required. But the impossibility doesn't diminish the value of the thought experiment. By translating kilometers into hours, miles into years, distances into durations, we've made the abstract concrete. We've taken numbers that slide past our comprehension and anchored them to something we understand. Time, measured in human spans, in the progression of years and decades and centuries that form the backbone of history. And perhaps, having completed this impossible journey in our minds, having accumulated 5,000 years of travel time to reach Neptune, having witnessed civilizations rise and fall while maintaining our steady pace toward distant worlds, we can look at actual space exploration with new eyes. The spacecraft we send to the planets don't just cross distance, they compress time. They take journeys that would require millennia at human speeds and accomplish them in years or decades through clever application of physics. Each mission represents not just a technological achievement, but a victory over the tyranny of distance, a refusal to accept the isolation that space imposes. When Perseverance roves across Mars, analyzing rocks and searching for signs of ancient life, it's doing so on a world that lies 61 years away at highway speed, decades of isolation compressed into a 7-month journey through orbital mechanics and chemical propulsion. The solar system revealed by our highway journey is a lonelier place than the maps might suggest. Those diagrams showing planets as circles spaced across a page don't convey the vast emptiness between them, the years or centuries of black void separating world from world. But it's also a more interconnected place than you might imagine, because we've reached across those voids repeatedly, binding the planets together not through physical proximity, but through the web of missions and observations and data that flows between our world and theirs. Every planet has been visited by human-made machines. Every planet has been studied, mapped, characterized. The highway doesn't exist, but the connections do, forged through radio waves and spacecraft, maintained through decades of patient observation. As we come to the end of this script, having spent tens of thousands of words exploring what it would mean to drive to each planet at highway speed, the answer echoes back clear and undeniable. It would take longer than we can spare, longer than civilizations last, longer than recorded history has existed. The planets are far, impossibly far when measured against human speeds and human lifetimes. And yet, we've reached them anyway, through patience and cleverness and the accumulated knowledge of centuries of physics and astronomy and engineering. The highway we've imagined is impossible, but the journey it represents, humanity's push into the solar system, continues every day. If you've enjoyed this cosmic road trip, this impossible journey, measuring out the solar system in years and decades and millennia, if these calculations have given you a new appreciation for the vastness of space and the remarkable nature of exploration, then perhaps you'll join us for future journeys into the cosmos. There are so many more questions to explore, so many more ways to make the incomprehensible comprehensible, to take the vast and make it relatable, to bridge the gap between astronomical scales and human understanding. This has been Nebula Nights, making the infinite intimate, one impossible journey at a time. The road through space is long, far longer than any we can travel at ordinary speeds. But the journey of understanding, of imagination, of calculated curiosity, that road is always open. And the destination, a deeper appreciation for our place in the cosmos and the remarkable nature of the universe we inhabit, is always worth reaching. Until next time, keep looking up. Keep asking questions. Keep imagining the impossible. The universe is vast, but our capacity to understand it, to explore it through both machines and mathematics, grows with every question we ask and every answer we pursue. If this journey through the solar system at highway speed has sparked your curiosity, if you'd like to explore more of the cosmos with us, please consider subscribing to Nebula Nights. Hit that like button if you enjoyed this deep dive into planetary distances and journey times, and share your thoughts in the comments. Which planetary journey surprised you most? Which distance challenged your intuition? What other cosmic scales would you like us to explore? Your engagement helps us continue creating these detailed explorations of space, time, and the universe we call home. Thank you for spending these hours with us, imagining the unimaginable, calculating the impossible, and discovering that sometimes the journey we cannot take teaches us more than the destinations we can reach. The highway to the planets stretches farther than any road on Earth, but the road to understanding, paved with curiosity and wonder, is always just beginning. Safe travels wherever your curiosity leads you next. The cosmos awaits, patient and vast, ready to reveal its secrets to those willing to ask the questions and pursue the answers, 1 mile, 1 hour, one question at a time.